There. Okay, so we're going to start today with some math-ish words. You know, if you're learning a foreign language, then you have to learn some vocabulary. And so the question is, what are these? What's the technical term, or what's the word for what these are?
Variable.
Variables. Now, what is a variable?
Something that we can assign a value to.
Excuse me?
Something that we can assign a value to. Or a placeholder.
Yes, it's something we can assign a value to, but doesn't have a value assigned yet. So it's a name for. This is sort of like name, what stands for. Say a synonym for number is numerical value. That sometimes that's the same thing. Numerical value is the same thing as a number. Okay, so it's a name for a numerical value that's not been chosen. Okay, so what about these? What are these? And a clue is that variables are by default. There's some conventions that make things simpler visually to recognize. For example, we recognize these are variables because they're from the end of the alphabet. And so what do you think these are? Excuse me?
Constant.
Yeah, these are constants. And the convention is, and you know, sometimes you just run out of symbols and you have to use, you have to make different conventions, but by default, we're going to think of these as constants. Now, constants are like variables, names for numbers that have been chosen. So this is just a name for a number that we've already chosen. Like they're just values that you sort of have. They're sort of part of the prerequisite of the problem that you. Let's see. Let me get there. Okay. Okay. So, what about? Let's see. Now, if I can put these things together, like 7x, 8x squared, or like a z to the -1, and these are all what we call terms. They're terms because they don't have any pluses. There's no addition. Okay, and they're all the form of some power of a variable. Like this is 1/z, x squared, x, with a numerical expression, like a number out front. Okay, we're going to be interested in just the ones like this. These are terms with just first power. You know, there's no squareds, no -1s, and these terms could have like multiple powers. Another term could be 7xy, and terms with these are just with one variable. First power, one variable. Okay, so we use these. We combine to make what we're after here are linear combinations. So a linear combination is a sum like 7x plus ay plus 9z, which is a sum of linear terms, right? So this is a linear combination, and that's sort of, you use that to make linear equations. But anyway, this is sort of the idea of this, that this is what linear algebra, this is a crucial concept, the idea of a linear combination. Okay, so but these are all expressions. They all are combinations of operator symbols and numbers They're all expressions that either have values in case of if we chose numbers for these, or could have values. Okay, now this thing here is an equation, right? It's a proposition or a claim. But let me start not from this, but let's say 2 plus 3 equals 7. So this is an equation, okay? It's either true or false. This one happens to be false. Now, so it's a numerical equation, right? And it's either true or false. Now, if I put an x in here, x plus 3 equals 7, it's still an equation, but it's not a proposition. It's not, since we haven't chosen a value for x, we don't know that it's true or false. So in the past, like in beginning algebra, you were given a problem like solve for x. But that's assuming that this equation is true, and you're just finding that x is a name for the value that makes this equation true. So we're taking a slightly different point of view and saying, well, we don't know if it's true or not. We want to find the value or all the values that make the equation true. And the reason we're taking that point of view is because we're going to look at many equations together, only some of which might be true. So that's just a point of view. Okay, so this is an algebraic equation, and it is not yet true or false. So it's not a proposition, not true or false yet. It will become a proposition once we choose a value for x. If we chose the value for x is 4, this would be true. But if we chose some other value like 5, it would be false. Okay. But there's different ways to make an algebraic equation true or false. For example, what about this one? X plus y equals y plus x. Well, this isn't true or false because we haven't chosen values for x. But what you're going to find is no matter what value you choose for x and what value you choose for y, the result will always be true, right? Because there's no way you can choose for any values you choose. So you can make a proposition out of this by saying for all numbers x and y, x plus y equals y plus x. Shruti?
Would x plus y equals y plus x be a logically equivalent proposition?
Excuse me?
Would it be a logically equivalent proposition?
What two propositions do you want to be logically equivalent?
Well, x plus y and y plus x.
Well, these are numerical expressions. Yes, you have to choose values. So what the equation says is, what this equation is saying, the numerical value on the left is equal to the numerical value on the right. But since we haven't, so it's more like a function. It's sort of like if I say f of x equals x squared, which is going to equal y, say, this isn't true or false. It's just saying I put in a number, I get out, like I put in 2, I get out 4, I put in 3, I get 9. So this is sort of like I choose numbers for x and y, and I get out a truth value. But here, I always, no matter what values I choose, I'm still going to get a true value. So this just shows that there's, this is one way of using this phrase for all numbers x and y. You're saying for all numbers x and y, x plus y equals y plus x. So that's a claim, and it's true. But on the other hand, if I said for all numbers x plus 3 equals 7, well, that would be a proposition. It'd be a claim, but it's false because you can, if I chose 4, it's true, but if I chose 5, it's false. So it isn't true for all numbers x.
That's a proposition, but
This is a proposition, but it's false.
But it wouldn't be a logically equivalent proposition.
It's what is.
It wouldn't be a logically equivalent proposition.
Okay, logical equivalence is saying proposition P and proposition Q have the same truth values. Yeah. So it wouldn't be logically equivalent to what? What's your second proposition you want to make it logically equivalent to?
Also, it can't be like x plus 3 is logically equivalent to 7.
Yes, this is a number. So this is numerically equal to, not logically equivalent is a relation. The words logically equivalent is a relationship between two different claims.
Sure.
It's like saying, let me, just since you've raised that issue, we will get to that. Let me see. 2 plus 3 equals 5, and 1 plus 4. Well, let me see. It's hard to, okay. So let's say if I have two propositions, P and Q, then P and Q is logically equivalent to Q and P. For example, if this one was, it's snowing, and this Q stood for it's raining, then this one says it's snowing and it's raining. This one says it's raining and it's snowing. Well, those two are they're two different claims, but they're logically equivalent, meaning that if they're either both true at the same time or both false. If one's true, the other one's true. If one's false, the other one's true, false. That's what logical equivalence means. So the relationships between a proposition or a claim, which is like equality, but it's equality between propositions, whereas this is an equality between numbers. Okay, so now we could make a different kind of proposition out of this claim here to say there is at least one X such that X plus 3 equals 7. That's a claim, right? And it happens to be true because there is a real number X, namely 4. Choose 4 for X. Doesn't have to be more than 1. Now, there are some equations where there could be more than 1, like you could choose X squared equals 1. Like, you could say the same thing. Now, it turns out that these phrases, there's at least one, and for all numbers X appear over and over again. And so the mathematicians use symbols for them that we'll sometimes use. And so the phrase for all numbers is written by an upside down A. See, there's the A here. So if you take an upside down A, this is what this means. It just means for all. So the phrase for all values X would be for all values X. So I could write this proposition up here as for all values X, X plus 3 equals 7. And of course, that's false. And so it's much easier if you have to write it many times to write this symbol than to write the phrase for every value X. And similarly, there's a symbol for this one, which is backwards E. And that's the same thing as it's sort of like there exists. Okay. And the exists is sounds sort of mystical, but it just means there is, there is one we can find. So, but the point is that the E here, you've taken the capital E and write it as a backwards E. So it's sort of in the symbol, it suggests the meaning that this is an upside down A for all. This is a backwards E for there exists. So I could make the similar proposition, there exists an X such that X plus 3 equals 7. So this vertical bar is also used as a symbol for the words such that. So even though this looks sort of cryptic or is compressed, you can read this as there exists an X such that X plus 3 equals 7 is true. So the equation we sort of think of as claiming its own being true. It's sort of like if I say x plus 3 equals 7, it's claiming to be true. Okay. So, and then up here, this comma is for every x, it is true that. So this comma sort of means here, it is true that. I'm only putting these sort of phrases in here so you can read something like this verbally. And one of the things when you come to this is, if you don't read it verbally, because it's symbols, you'll just see the things that feel familiar, but it won't really create any thought in your mind. And so it's easy to sort of like get confused because you're seeing it as being familiar, but not really. Okay, so the problem is here, we need to make some statements that are precise. And that's why we're introducing some of this extra sort of language or technology so that you can we can make some precise statements. And because there's a bunch of stuff in linear algebra that's more sort of precise, and you have to sort of develop that mindset. It's not that different from treating programming concepts in which you have a programming language and the instructions mean very specific things that are suggested by the symbols and words, but that aren't exactly what you would think intuitively. Now, there's some rough edges here and there. Okay. So what, and of course, these two things work for any claim, for any, you don't have to have these particular ones. So you can have general claims. Okay. So this is just some refreshing, introducing some words that you have probably heard your math instructors use before, but that you weren't ever, that weren't ever salient, or you sort of heard them, but then you could essentially ignore them if you wanted to. And here we're just going to take pay a little more attention to some of these words. But realizing it can sort of we don't want to go overboard too much and sort of overwhelm you with all these different words.
There exists. Does that mean that there's at least one, or does it mean there are many?
There's at least one.
So you can so there are two.
Yes, you could. There could be two. There could be three. But it's sort of like the extremes: either everything or at least one.
Okay.
Because if you know there's at least one, you can sort of work with that. And there might be more, and usually there are. But then it's in some cases, and so. Somehow those two cases, those extreme cases are really important. Whereas the case of, if there exists two solutions or two values doesn't seem to have as much sort of logical importance. Okay. So then what else? Well, we have the idea of, so this is sort of up to, now the thing is what all of the math stuff that goes on in this text and elsewhere is all about the relationships between different claims, say between equations. So there's different ways that you can combine equations or propositions to make compound propositions or relationships. And let me introduce some of these. For example, if I have two propositions P and Q, these letters just mean that you could think of this as like an equation. If these two things are, we can combine them with an and symbol. And there's a logical symbol for and like this. You can think of this again as like the and without the little crossbar, right? There's the A here, and this is sort of like the A without the little crossbar as a mnemonic. Now, this is true. So if this P can be true or false, Q can be true or false. This is only true when P is true and Q is true. So it's like a conjunction. It's saying that this is only true when they're both true. Okay, and now this is actually used in a linear system, because if I have a linear system, I have, say, 3x plus 5y, there's a linear combination that's equal to 7, and 2x plus 8y equals 6. Well, these are two claims. And what makes it a linear system is the solution set is the claim. Let's say that I have two numbers, Sx, a value for x and a value for y. I have these two numbers, and I say this is a solution of this system, which means if I choose S for x, if I choose Sx for s and S sub y for y, then both of these equations are true. So what I can say is the set of all solutions is going to be all these pairs. Say, let me just do it. So instead of x and y, it's hard to read. S1, S2, such that there's this vertical bar again, right? Such that 3x plus 5y equals 7 and 2x plus 8y equals 6. So this is sort of a way of saying this is the solution set. It's the set of all these pairs of numbers that make both equations true. So this isn't very helpful. It's not very insightful. In fact, what Gauss's method does is, because there's all these connections, you can't really see it. The Gauss's method is aimed at making this into a logically equivalent claim that's much simpler. Okay, so what we're going to do is Gauss's method aims to make a much simpler solution set, and the way that we did the solutions last time was of that form, because we sort of ordered the equations so we could parameterize the solutions. And we're going to go back, and after this little snippet here of like precision, we're going to go back and practice what we did last time.